How is the periodic table arranged for finite elements? Have you ever wondered how the periodic table of finite elements is structured? It is a fascinating topic that combines mathematics and science. Let's break it down together. The periodic table for finite elements is a visual tool that organizes finite element spaces based on their mathematical properties and mesh types. Unlike the traditional chemical periodic table, which sorts elements by atomic number and chemical behavior, this table focuses on families of function spaces used in numerical methods. At the heart of this arrangement are four main families of finite elements. The first family is the simplicial mesh families. These are based on shapes like triangles in 2 dimensions and tetrahedra in 3 dimensions. Within this family, there are 2 groups. The first group is known as the polynomial differential forms with specific continuity properties. The second group is closely related but differs in terms of approximation, order, and smoothness. Next, we have the cubical or box mesh families. These are based on cube or rectangular shapes. One group in this family generalizes simplicial elements to cubical domains. Another group is known as serendipity elements, which reduce degrees of freedom while still maintaining quality and approximation. Each finite element space is represented as a box in the table. The arrangement is systematic, with rows and columns that correspond to increasing polynomial order and differential from degree. This layout helps reveal relationships between different finite elements, much like how the chemical periodic table shows trends in element properties. The arrangement of the finite element periodic table is closely linked to a mathematical framework called finite element exterior calculus. This framework uses differential forms to clarify the properties of these elements. Historically, it has brought order to what was once a chaotic collection of finite element types. This organization has led to the discovery of new element families and improved numerical methods for simulating physical phenomena. Scientists and engineers use this periodic table to select the right finite elements for computational simulations. These simulations are crucial in fields like physics, engineering, and applied mathematics. They help solve complex problems such as fluid flow, structural analysis, and electromagnetic fields with greater accuracy and efficiency. The periodic table of finite elements is more than just a chart. It is a significant milestone in the mathematical understanding and practical application of numerical methods in science and engineering.